Welcome to the final lecture in our course, Lecture 36. Today we want to ask a question that seems to crop up at the end of centuries. The question is this: is there an end to science? Are we getting close to wrapping up our knowledge of nature? Will we arrive at a final theory? I say that this question crops up at the end of centuries because, as we'll see in this lecture, it came up at the end of the 19th century, and it also made its appearance at various points in the last century, the 20th century. In 1996, there was a book called The End of Science, Facing the Limits of Knowledge in the Twilight of the Scientific Age. We're obviously going to focus here on the 19th century story, and we'll use it to wrap things up in this course, which ends with the close of the 19th century. But as we do, we won't be able to resist looking ahead just a bit to the new century. Throughout this series, we've encountered a number of occasions when natural philosophers and scientists encountered results that appeared to be inconsistent with the mechanical model of nature they'd been perfecting. If at the beginning of the 19th century there had been a competing vision of nature in which organism, not mechanism, was seen as the better metaphor for nature, that competing vision of nature found itself more and more on the defensive as the 19th century proceeded. Especially with the emergence of the conservation of energy around mid-century, it became harder to carve out a place where the phenomena of living things could be seen as exceptions to the physical forces of chemistry and physics. Not that some still didn't try, but they were fighting a mechanistic image of natural science that captured a lot of attention in the public sphere. That image, for example, was promoted by the scientific materialists, for whom there was no question at all that scientific explanations consisted of discovering nature's mechanisms. One German thinker, as I mentioned, went so far to say that mechanics and logic were identical. We heard that from Wilhelm Wundt in an earlier lecture. So the mechanical view of nature reigned supreme in the minds of many, even if they interpreted the philosophical implications and limitations of this vision of natural science in various individual ways. This is not to suggest that there hadn't been warning signs, that the so-called Laplacian world machine might not be the last word on the subject. We've run across numerous examples of what, in retrospect, we can recognize as warning signs. In Lecture 26, for example, I noted that Ørsted uncovered magnetic force that acted in a circle around a current-carrying wire. The magnetic force didn't act in straight lines, as Newton's forces were supposed to. And in Lecture 27, I pointed out that Joseph Fourier's description of heat flow as irreversible, moving from hot to cold and never the other way around, was in a sense incompatible with mechanical explanation. Mechanical forces were normally understood to be, in theory, reversible. That is, you could easily imagine a machine running backwards. But Fourier was saying that this couldn't be where heat flow was concerned. Then in Lecture 30, William Thomson's idea of the dissipation of energy. That's where energy is still present, but it has become unavailable to do any work. This dissipated energy also accumulated in one direction only. How is one to give a mechanical account of that when mechanics ran equally in both directions? And what about the need in the kinetic theory of gases to assume nature behaves statistically? That challenged the idea of a deterministic world machinery. Finally, last time in Lecture 35, Maxwell's successful depiction of light as waves in a mechanically acting ether resulted in an enigmatic ether that was neither at rest nor moving with respect to the Earth. As I said, in retrospect, we can see that these were all warning signs that the mechanical view of nature had its limitations. But that's not fair. We're not supposed to do history in retrospect. If we try to look at these exceptional developments in the way they were regarded by members of the 19th century itself, we'll see that they didn't regard them as warning signs of anything drastic at all. The first thing they noticed about these innovations was that they worked. Sure, they led to problems, but they permitted scientists to explain more and to make accurate predictions. For example, you couldn't deny that scientists had learned to understand a great deal more about electricity, magnetism, and light as a result of them. And they also applied what they learned to make new electrical machines that began to supply useful energy to society. Further, they led to revolutions in communication. Think of what lay ahead for radio. And they made possible new ways of lighting public spaces that were visible evidence to everyone in society of the practical value of what scientists had learned. As a result, scientists didn't tend to regard any inconsistencies and paradoxes they encountered as fundamental problems. I'm sure they figured that someday their successors would solve these bothersome features of their explanations, but they didn't regard them as challenges to the mechanical worldview of nature that had worked so well since Laplace's day. In fact, scientists grew very proud of the strides they'd made, and that made them confident that they were doing something right. It even made a few wonder if science was nearing the completion of its task of describing nature. In this lecture, I want to look at the growth of this confident attitude about natural science. It was based on the wonderful things that had been achieved, and it appeared among some in the late 19th century. We'll end the course with two developments that would challenge this confidence at its core and point toward unknown territory for natural science in the new century to come. Let's take a moment to review why scientists had a right to be confident. They were indeed learning more and more of nature's secrets. Just look at the accomplishments of the 19th century alone. Take first the biological sciences. There were a lot of reasons for confidence there. Think about it. By the end of the century, the understanding of life's past was vastly different from what it had been back in 1800. Sure, there were disagreements about natural selection, but there was less and less doubt about the reality of evolution. And that meant that people thought of humankind differently from how it had been viewed from the dawn of history. Most people felt that their age was special. They were living in the time when the truth about the vast history of the cosmos and of living things had finally become widely acknowledged. And think of the advances in medicine that allowed scientists like Pasteur to step out of his role as a technical scientist and become a hero who bore testimony to the value of natural science. Physicians were more and more aspiring to something they called scientific medicine. They were increasingly beginning to associate themselves with scientists. All these developments had led to a situation in which natural science had come to lay at the heart of burning social and political questions that used to be the prerogative of powerful political leaders alone. But now, questions of public health, questions of how society should be organized to be in sync with nature, questions about how the human race could become strong in the struggle for existence, all these demanded involvement of scientists. And what about the physical sciences? Here the strides in our knowledge of nature were equally impressive and significant. From those early attempts to understand the interaction of nature's many forces came a comprehensive understanding of energy in the universe. It was an understanding that bore implications for the end of time that influenced philosophical and religious worldviews. And these were no mere armchair deductions of interest only to technical physicists. They permitted popular declarations about a materialistic universe that spoke to our understanding of the very meaning of existence. New telescopes brought the heavens closer. Knowledge of the vastness of space grew. Humankind saw itself in a different physical light, just as it had in a new biological light. And where all these questions were concerned, the scientists began to replace the parish priest or pastor or rabbi as the source to which you turn to find the answers to age-old questions. That was a major difference from the beginning of the century. It was as if there'd been this massive transfer of social authority from the local pastor to the public figure known as the scientist. By the end of the century, you knew if you were a local priest or a rabbi that you were out of your element if you said anything too specific about the workings of nature. For their part, some scientists became so confident about what had been achieved that they began to feel that they had finally discovered the tools to finish the work of understanding nature. They believed in something I'm going to call scientific realism. That's the notion that scientific theory is able to depict nature as it really is. This suggests that when scientists employed hypothetical entities, say molecules, for example, they believed that these entities were more than merely hypothetical. They were real things. And they were not alone in thinking that. It was typical of the general realism of the day. Some were impressed with how far natural science had come compared to what people used to think about nature in the past. They were confident that science had identified a unique method. It was based on careful observation and experimentation, and it would lead humankind ever closer to nature's truth. One physicist put it this way, that nature's truth was like a mathematical asymptote. That's a line which a curve approaches closer and closer to without ever touching it. Human knowledge, he said, was like the curve, and we're getting closer and closer to nature's truth, although we'll never be able to say that we've actually achieved it all. To this kind of individual, the cosmos was the clockwork universe that had been so celebrated by Laplace. It was a realm ruled by deterministic law. To explain something scientifically meant to take apart nature's machinery and see how it worked. So given the success of mechanical models in kinetic theory and electromagnetism, given the unifying power of the new concepts of energy and the field, no wonder they were confident that persistent problems would someday be resolved. And no wonder that some became convinced that physical science might be coming near to its end. While confidence in mechanistic natural science grew to impressive levels in some circles during the late 19th century, let me give you a few examples of what I mean. In 1887, the soon-to-be president of the American Association for the Advancement of Science said the following, and I quote, "More than ever before in the history of science and invention, it is safe now to say what is possible and what is impossible. No one would claim for a moment that during the next 500 years the accumulated stock of knowledge of geography will increase as it has during the last 500. In the same way, it may be safely affirmed that in electricity, the past 100 years is not likely to be duplicated in the next, at least as to great original and far-reaching discoveries or novel and almost revolutionary applications." Note these words. We can safely conclude that there won't be any novel or revolutionary applications in electricity in the next 100 years. Why? Because of what we've done in the last 100. Nobody can match that pace. Look at what we've achieved. It's like geography. We've learned so much about our globe in the last 500 years that it would be impossible to duplicate that much knowledge in the next 500. There's not that much left to learn. Well, in 1894, Albert Michelson, the same one who conducted the famous ether experiment, said something that really captured this idea that there's not that much left to do. Listen to what he said as the century wound down. "It seems probable that most of the grand underlying principles have been firmly established and that further advances are to be sought chiefly in the rigorous application of these principles to all the phenomena that come under our notice. An eminent physicist has remarked that the future truths of physical science are to be looked for in the 6th place of decimals." The implication here was that we have the basics of nature down pat. What's left to do is to make what we have more precise, clean it up to the 5th and 6th decimal points. And scientists weren't the only ones who had this attitude. Some theologians shared this image of science nearing its end. My favorite example of this is a theologian who was asked why the Protestant Union was not putting together a new confession of faith. He replied that it was because natural science and philosophy had not yet completed their work. It was as if he was saying, we'll wait for them to finish up, and then we'll revise the confession. No sense in being premature about it. Well, these attitudes might strike you as naive. That, of course, is our judgment from the present. But there were also those from the period itself who didn't share this optimism and confidence in mechanistic science. I can tell you that Maxwell, although he certainly believed in an ether that possessed mechanical properties, Maxwell was hesitant to embrace his particular model of the ether as something that actually existed. It was his Scottish religious outlook that warned him, I think, against too much pride here. These things may be more complicated than we have any idea of. Best not to commit ourselves too quickly about how final our present state of knowledge is. And physicists like Ernst Mach, you know him from the measure of the speed of sound that bears his name, Mach 1, Mach 2. Ernst Mach began to reflect about the nature of scientific theory, suspecting that what I've called scientific realism was a flawed way of understanding it. And he wasn't alone either. Others, like the physicist Pierre Duhem, the mathematician Henri Poincaré, the philosopher Hans Feinger, each one, in his own different manner, moved away from the simple claim that scientific theory represented nature as it really was. Each one, in other words, began to challenge what we've called scientific realism. And there were always those warning signs we've identified, whose presence, if not noticed as warning signs, seemed to have lodged at least in the subconscious minds of some scientists. The inconsistencies about the ether that Michelson and Morley had exposed stared everyone in the face. Some shrugged them off, as I said, but others didn't. William Thomson, by now Lord Kelvin, referred in 1901 to the clouds that hung over physical theory. That's not what I'd call a cocky attitude. Well, as the new century dawned, two major developments, quantum theory and relativity, made their appearance on the horizon. And as they settled in and began to be accepted as bona fide new outlooks that had staying power, they seemed to undermine the clockwork universe and the optimism and confidence we heard in those two earlier quotations I gave you from the 1880s and 1890s. And in so doing, they also challenged at its core the attitude of scientific realism. The first of these developments emerged from the work of the physicist Max Planck. Planck challenged a fundamental assumption that natural philosophers had held for ages, that change in nature occurs smoothly. In the late 19th century, it was expressed in terms of energy. There it ran like this: changes in energy, when it's given off or taken on, occur continuously. That's the way we see things, after all. Our perception of natural processes that require energy is of smooth or continuous change. When we see a car accelerating from 0 to 50, we assume it passes through every possible velocity between 0 and 50. Now, Planck was engaged in a project to map the energy radiation that occurs when a particular kind of body was heated from lower to higher temperatures. He and everyone else assumed that the variations in the output that would be observed would occur smoothly and continuously. The hotter the temperature, for example, the greater the energy. That was what you might expect. But the problem wasn't quite that simple. The results were more complicated than many had anticipated. They were so complicated, in fact, that no one was able to give a complete account of the energy pattern from low to high temperatures. The middle range temperatures were especially problematic. Well, Planck eventually solved the problem, but his solution came at a price. It involved abandoning the assumption that energy had to be radiated continuously. But what would that mean? Well, Planck introduced the idea of quanta, or permissible discrete amounts of energy. Quanta were packets of energy whose size is determined by the frequency of the radiation. When energy was radiated or absorbed, it was as if it happened in little pellets of energy of various permissible sizes. That meant that it didn't happen, nature didn't allow it to happen, in pellets of other sizes. So there was good news and bad news here. The good news was that using this revolutionary idea, Planck was able to be successful in his description of the overall energy pattern from low to high temperatures. But there was bad news too, and the bad news was, if nature behaved the way Planck described it in this context, then it was as if the car accelerated by going from, say, 0 to a ½ mile per hour without ever passing through a ¼ mile per hour. This is like magic, since the car seems to disappear from its first state of rest and reappear at the second state of ½ mile per hour. Of course, it would take quite a while before anyone was willing to say that nature was really like Planck's theory implied it was. But at least one could say that nature was better described using his notion than by the older classical understanding of energy change as continuous. Of course, too, you wouldn't want to jump to conclusions about giving up the classical idea of energy change just on the basis of these experiments of Planck around 1900, but it wasn't that long before Planck's idea of quantizing energy began to find applications in other areas of physics. And when that happened, physicists began to take seriously that perhaps nature did indeed behave in such a bizarre fashion. If it did, then gone was the intuitive idea that nature was a deterministic machinery whose laws were within our grasp. The picture of nature physicists began to embrace was more revolutionary and new than maybe even Newton's had been in the 17th century. What was happening was exactly what the president of the American Association for the Advancement of Science had said in 1887 couldn't happen anymore, that there would be great, original, and far-reaching discoveries or novel and almost revolutionary applications. So quantum theory was one of the developments that raised its head at the beginning of the new century. It would take several decades to work out a system of quantum mechanics that would replace classical mechanics and its deterministic worldview. But there was also another development that shook physics to its core at the beginning of the 20th century. Clearly, I'm referring here to relativity theory. And that revolution came about not so much from thinking about the heavens, where we're used to thinking about relativity theory, as it did from 19th century electromagnetism. And it was because young Albert Einstein insisted that all the laws of physics were the same for everyone. Let me explain what I mean. When the thinkers of the 17th century introduced the idea that there was a kind of motion that was equivalent to rest, we call it inertial or uniform motion, they were saying that the mechanical laws which we find work in a frame of reference that is at rest will also work for a frame of reference that is in uniform motion. You can generalize this by saying that the laws of mechanics are the same for all observers in uniform motion. So if you're in uniform motion and you have no way of comparing yourself to another frame of reference, you can't tell whether you're moving or at rest. Now remember that. I'm going to come back to it. Note that all this has reference to the laws of mechanics. But what about the laws of electromagnetism? Would the implication about the laws of mechanics being the same for all observers in uniform motion apply to the laws of electromagnetism as well? Would the laws of electromagnetism be the same for all observers in uniform motion? Well, Einstein was convinced that the laws of electromagnetism were like those of mechanics in this respect. He believed that the laws of electromagnetism would also be the same for all observers in uniform motion. All the laws of physics were the same for observers in uniform motion. But would this lead to some strange results and another challenge? You bet. It led to a challenge of the realistic attitude that many 19th century physicists had. Now, Einstein was no doubt aware of the problems raised by experiments with the ether. But as I said, his real motivation came from a different source, from a concern to show that the laws of electromagnetism were not inconsistent with the laws of motion. As a boy, Einstein had read a series of books called Popular Papers on Natural Science. The author, Aaron Bernstein, caught his attention by vivid descriptions of the way scientists thought. In one case, Bernstein invited his readers to go with him on a journey to visit the planets. To get there, he suggested riding on an electric signal through space. He said if we took any conventional means, like a horse and carriage or even a locomotive, it would take us forever to make the tour. So it was better to go on something that was moving very fast, and an electric signal was just the thing. Later in his life, Einstein took up this idea of riding on an electric signal. In his case, he asked himself what the world would look like if he rode on a beam of light, one of the very beams by which we obtain information about the world. Well, he thought about this and concluded that if he traveled as fast as the light on a beam of light, he wouldn't be able to see anything ahead of him since the light couldn't get in front of him to be reflected back from objects up ahead. Now, that would only happen when he was going the speed of light. So he had effectively developed a test that would tell him absolutely that he was not at rest. And he'd done it from within his frame of reference alone. But remember what I said about the laws of mechanics? That if you're in uniform motion and have no way of comparing yourself to another frame of reference, you can't tell whether you're moving or at rest. So by using this thought experiment about light, Einstein was able to conclude that the laws of electromagnetism were apparently not like those of mechanics. But that was something Einstein didn't want to be. He wanted all the laws of physics to be the same for observers in uniform motion. How to get out of this dilemma? Well, to ensure the consistency of all the laws of physics, Einstein declared that light's speed was absolute, that it would not show differences from one observer to another. In other words, even if he were traveling at the speed of light, as in his thought experiment, he would be able to see objects ahead of him, since the speed of light relative to him would be the same as it was relative to all observers, regardless how fast they were going. So, since he would see objects ahead of him, he'd be just like the case of people at rest, who also would see objects ahead of them. Even if he were riding on a beam of light, he wouldn't know whether he was moving or at rest. All this meant that light's speed did not change to accommodate different frameworks of space and time. Rather, it was the other way around. Space and time changed to accommodate the constancy of light's speed. Now, the idea of changing space and time was not an easy one for classical thinkers from the 19th century to get hold of. But when it began to look like Einstein's idea of special relativity was here to stay, the old world of 19th century physics was presented with its second example of a great, original, and far-reaching discovery that had been declared impossible in 1887. So you can see that what I've called scientific realism, the idea that our theories describe accurately the way nature really is, while not eliminated as a possible position, was made much more difficult to hold by developments at the beginning of the 20th century. And as you probably know, the challenges would simply get worse. As quantum theory and relativity developed into full-blown theories of their own, they were found to contain within themselves paradoxes that were just not acceptable to some from the old school. Natural science was not supposed to tolerate contradictions of the kind that began emerging as the new century unfolded. And the challenge to an older, comfortable realism in natural science was accompanied by other breakdowns of realism in other areas around the turn of the new century. Realism in art and literature gave way to new forms, strange new art forms, that clearly abandoned the value of trying to depict the world as it really is. Even in the world of politics and diplomacy, where the principle of realpolitik, power politics, real politics of reality, where that had reigned, things were beginning to go awry there as well, only to collapse with the outbreak of World War. But for natural science, all these developments contained a very silver lining. The decline in the deterministic mechanical world picture of the clockwork universe and its replacement with the exciting and wide-open world of relativity and quantum theory really just confirmed an old lesson from the history of science. And that is that there's no end to science. Natural science is a continuing adventure in which one ought never to assume that the last word is even close to being spoken. Natural science changes as we do, and we are still largely mysteries to ourselves. In fact, it's on this idea of the necessity of mystery for science that I'd like to close my time together with you. It's been a great ride, and I've enjoyed it immensely. I want to thank you for sharing it with me. There's no better way to end than to quote one of the greatest representatives of natural science that we have, Albert Einstein. Here's what he said: "The most beautiful experience we can have is the mysterious. It is the fundamental emotion that stands at the cradle of true art and true science. Whoever does not know it and can no longer wonder, no longer marvel, is as good as dead. Thank you very much.